Welcome to the fabulous room 1065. It's a Kelvin Dueck physics show extravaganza, sponsored by Gravity. It's effing great.
Gravity, it's the law. Gravity makes a great Valentine's Day wish because we're all attracted to each other. Valentine's Day coming up, folks. I'm telling you, nerd Valentine's cards. They'll make the little girl's heart and the little guy's heart go pitter-pat. Number one, hey, this is an Atwood machine. So given the following massless, frictionless pulley, that's what an Atwood machine is to make the math nice, where M1 equals and M2 equals, find the acceleration. All right, I'm going to start up by labeling the forces. I have M1G, gravitational force down, tension up, M2G, tension up. Who's winning? Whichever one of these is heavier. Whichever one of these has more mass. You know what? That's the winner. Barely. So I'm not expecting a big acceleration. In fact, if they were tied, if it was 21.3 kilograms on either side, I'd expect no acceleration. Oh, and there's a built-in error check. I can't possibly get an answer bigger than 9.8. If that happens, I've typed something wrong on my calculator or done something wonky. So although this is still tricky, there are at least some parameters that I can kind of roughly... Okay. So who's winning? I think my equation's going to look like this. Winner minus loser plus winner minus loser. Down on the left is winner, so up on the left is loser. This tension, you might think because it's up, it's a winner, but when it ends up on the left-hand side, it does end up pointing down. It's a loser, and you might think that M2G, because it's down, is a winner, but actually when it ends up on the left-hand side, it ends up pointing the loser. And I've written forces from more than one mass. I better have more than one mass. Tension canceling? Excellent. They want to, how about I get the A by itself? I think divide by the bracket. I think A is going to be M1G minus M2G all over M1 plus M2. I think A is going to be 21.3 times 9.8 minus 19.6 times 9.8, all divided by 21.3 plus 19.6. A is going to be pretty small. Bracket 21.3 times 9.8 plus, Mr. Dueck? How about minus Mr. Dueck? 19.6 times 9.8, close bracket, divided by bracket 21.3 plus 19.6, close bracket. Do you get 0.407? 0.41? I guess 3 sig figs, looking at the 21.3 and the 19.6. So I'm going to go 0.407 units. Meters per second squared. How many marks was this question worth? 4. Conveniently, 1 line, 2 lines, 3 lines, 4 lines, and a half mark off if you botched the units or forgot the units. What's the answer actually worth? 1 mark out of the 4. Why? I'm really far more concerned with the method, with the process, with teaching you guys how to analyze physics analytically. B, find the tension in the cord. Okay. I'm going to use mass 2 because in mass 2, tension is winning, and it'll give me a prettier equation. You can do this with mass 1, and if you get the same answer as me, you'll get full marks. So in mass 2, I would say to myself, winner minus loser equals, and I'm only looking at mass 2, M2A. I would plus the M2G over. I would say, hello. Come on, pen. Okay. Pause the video for 1 second. We're back. I'm going to plus the M2G over, so I'm going to get tension equals M2A plus M2 G. If you used mass 1, I think you're going to get tension equals M1G minus M1A, I think. Tension equals M2 19.6, A 0.407, although I'm going to use the answer thingy on my calculator, plus 19.6 times 9.8. 19.6 times answer button plus 19.6 times 9.8. 200? Even? Yeah. Is that a fluke? I'll take it though. By the way, technically, I should go to 3 sig figs, so technically I would have to write that, but 200 newtons I'll take. And it's tension, newton is a force. Pardon me? Or 200 decimal. Touche. I always forget about that one because that's much more of a chemistry convention. Number 2. Looks like they're wanting me to find a force. You know what? I think this is a job for a free body diagram. Since they didn't give me a picture, I think I'm going to say, here is my skier. Mr. Dueck, can you do that lovely stick figure skier that you did on the last quiz? Oh, no, but thank you. I'm flattered. There. Little ski full? No? For me, that's good. What are the forces? Oh, thank you, thank you. Oh, hang on. My bad. Forgot to sign it. Okay. What are the forces acting on this skier? Get the obvious one. Is the skier sinking into the ground? No. Is the skier lifting into the air? No. What else? Definitely it's talking about friction, and since I've drawn the skier moving to the right, I would assume that friction is acting to the left. What else? Well, the key word, of course, I didn't underline this time on purpose, but I'm hoping you see it underlined. Constant speed tells me there has to be a force this way, and it has to be the same size as friction. Now, you know what? I think that's the applied force. That's the ski poles. Who's winning? Well, technically it's a tie, but you could certainly say to yourself, Shaq, well, he's moving to the right. You could say the applied is the winner, friction is the loser, equals MA. But then you would say to yourself, hey, A is 0, because it says constant speed. In which case, you could say, in fact, what you could really say is, and if you jumped straight to that line right there, great. I have no problem with that. They want me to find the applied force. I can't. But look. I know another force the same size as the applied force. Which force? Friction. So now I say to myself, friction is what times what? Mu times the normal force. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. All this is to say, I think that the applied force is going to be equal to mu mg. It's going to be equal to 0.147, 9.8. Okay. By the way, this means if you're an Olympic cross-country skier, it's worth losing weight because the lighter your mass, the smaller force you have to exert to overcome friction. Okay, that's why you don't see a huge fat Olympic champion cross-country skier. Even if they could get the cardio and the muscle system, it would still be a big handicap. The applied force, what was that? 50.666. I'll go 50.7 or 51 newtons. If you get that, you got 3 out of 3. Otherwise, I'd probably go something like this. I'd give you 1 mark if I saw F applied equals friction. I'd probably give you 1 mark if I saw F applied equals mu mg. And then I'd probably give you 1 mark for the answer. And then I'd turn the page. Is it turn the page or next page over?
Turn the page.
Turn the page? Okay. Consider the 12 kilogram mass below. What would be the acceleration of the mass? Assume there is no friction. Okay. Who's winning? 60. Who's losing? Okay. Uh, 60 take away 36, 24. And how would I get the A by itself? Divide by the mass. So I'm going to divide by the mass. And the mass is 12. You know what? I can do this in my head. 24 divided by 12. 2 meters per second squared to the left. Consider the following diagram. There's an applied force, there's friction, M1 equals 100, 1 times 10 to the 2. Free body diagram, okay. Gravity, normal force, applied, friction, okay. To get full marks, I would look for a half mark for each one of these arrows, but I would also say normal and gravity have to be the same length, and I would say I think applied ends up being longer than friction because I'm pretty sure you get an acceleration in part B. So a half mark for each arrow to get 2 marks, but also the scale has to be kind of accurate. Stuff that's the same has to be the same. Yeah?
What was 3 out of?
So 1 mark because it's multiple choice. Yeah, I think it makes sense too. I would have figured it out. It's okay. You're special. Right? Mu times the normal force equals ma. You know what? I can get the A by itself by dividing by m. And that's going to be F applied minus mu. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Woohoo! mg. And now I think I've got it to the plug and chug stage. A equals 225 minus. I'm going to make a mistake on purpose. See if you spot the mistake on purpose. What's the mistake? Well, I forgot the normal force. I got to be fussy, which happens to be gravity. I see a lot of students, when they think force of friction, they just write mu, which, by the way, being 0.5 is really small and hardly going to change the question, which is a whole other issue. But they get mu, the coefficient of friction, the decimal that describes how sticky the surfaces are, confused with a force in newtons of friction. And I'm sorry, a force in newtons of friction is always mu times the normal force. And Ben, that's why I will almost always walk through this substitution. I don't take too many shortcuts. It's far too easy to get sloppy and forget stuff. In fact, it was in this class. No, I think it was in my other block where I had a student showing me their quiz and saying, Mr. Dueck, what have I done wrong? And they'd had just the 0.15 there. And I see that all the time on the test. I see that all the time on the quizzes. Don't do that. It's a force, and the whole force, the expression for the entire force, has to go there. We're going to get bracket 225 minus 0.15 times 100 times 9.8, close bracket, divided by 100. Do you get 0.78? That seems wrong. Is that right? Oh, it is? Oh, it seems really small. Okay. Meters per second squared. If you got that right, 2 out of 2. Otherwise, I'd give you a half mark if I saw that. I'd give you, of course, a half mark for the answer. I'd give you a half mark if I saw that line right there. And I'd give you a half mark for successfully sticking in the numbers. And that's it, I think, yes? Can you give yourself a nice clear score out of, count 'em, 15? So we've said this. Gravity universally, now on the Earth as a shortcut, you can just go mg using the 9.8. But if you want to calculate it anywhere in the universe, or you want to calculate it a certain distance away from the center of the Earth, up in orbit, up in outer space, it's big G, where G was that strange gravitational constant, 6.67 times 10 to the negative 11. That was the number that had to go in front just so you got an answer in newtons. Times mass 1 times mass 2 divided by the square of the distance between them. I said gravity is usually minuscule unless one of the masses is huge. For instance, a planet or a star or a moon. Example 4. Assume that the mass of the Earth is 5.98 times 10 to the 24th kilograms, which it is. And its radius is 6.380 times 10 to the 6th meters, which it is. Then find the force of gravity that the Earth exerts on a 50-kilogram person on its surface. Oh, and you can ignore the size of the person compared to the radius of the Earth. So you might say, shouldn't I add 1 meter because the person's about 1 meter tall? Well, if you add 1 meter to 6.38 times 10 to the 6th, you're going to get 6.38 times 10 to the 6th, basically. So let's calculate the force of gravity. That's going to be big G, big M, little m over r squared. Now, I've made the equation look a bit different, Jeff. Last day it was m1, m2. It's traditional when you're talking about a planet and something orbiting the planet, use a capital M for the planet and a little m for the little mass. So I tend to do that, especially in Physics 12. So you can think of that as m1 and m2. But without thinking about it, I'll almost always go big M, little m, as soon as we're dealing with a big mass and a little tiny mass. Oh, and since the Earth is shaped like a circle, I'm using r for radius instead of d for distance. But it's the same idea. It's going to be 6.67 times 10 to the negative 11. Big M, mass of the Earth, 5.98 times 10 to the 24th. Little m, mass of the person, 50, divided by radius of the Earth squared, 6.38 times 10 to the 6th squared. And that's worth practicing typing into our calculator because it's a fairly complicated expression with lots of scientific notation. So try it and see what you get. Can I do this in my head? Sure I can. I think. Yeah? No? Yeah? Of course, I didn't do that in my head. I used a shortcut. I did it in my head, but I used a different method. But you want to see if you can get the 490 newtons. And it's like 489.99, or it is exactly 490. 89.99, really close, right? Okay. And if you can't get that, now is your chance to ask, and I'll help you with your calculator. Okay. By the way, you know how I did it in my head? Is this person standing on the Earth in the diagram? Then I can also calculate the force of gravity by going m little g. I went 50 times 9.8. And that I can do in my head. And so this answer of 490 shouldn't surprise us because it's the same that we would get if we went 50 times 9.8. But the fact that I do get the same answer helps convince me that the other big universal equation, it's right, because I haven't really done a proof of it with you. I've just said, this is what he said. So I wrote here, this really shouldn't be surprising, because if I calculate the force of gravity, since we're on the Earth, using our shortcut method, mg, I also get 490 newtons. That actually has some profound implications. So up until now, we've had two ways to determine the gravitational field strength of a planet, by the way. The Earth's gravitational field is 9.8 9.8 what? Meters per second squared, or newtons per kilogram. The Earth's gravitational field is 9.8. Now, we haven't called it that all year. All year, we've said, what's the acceleration due to gravity? But it turns out when you say acceleration due to gravity, I can say gravitational field strength, because the acceleration due to gravity is because of the Earth's gravitational field strength, and they're one and the same magnitude. And you can think about it in terms of a acceleration, but you can also think about it as in terms of a force divided by mass, newtons divided by kilograms. Turns out meters per second squared and newtons per kilogram are the same units fundamentally, just written differently. So there's two ways to get the gravity field strength. One way is on the Earth to hang a mass from a Newton scale and read the force. I know the force, divide by the mass, and that gets me g. So if you were on the moon, you could take a 5 kilogram mass, hang it from a Newton scale, and to find g on the moon, whatever the scale read, divided by 5 kilograms, and you would get g on the moon. That's one way. The second way is the experiment that we did in the little alcove over there where you were all dropping objects and timing their free fall. If we were more accurate, we could have got the 9.8 that way. We were way off because we had human reaction time. But up until now, we've had two ways to find gravitational field strength. So number one, the gravity field at a point can be determined by measuring the weight, mg, of a small mass, m, and dividing the weight by the mass. That gives you the 9.8, or whatever planet you're on. The gravity field can also be determined by measuring free fall acceleration. So if you were on the moon and you dropped something and you had a stopwatch and you started it and stopped it, you could also calculate g on the moon. If you were on Mars, you could calculate g on Mars. We now have a third way. Okay, so here's the first two ways. We have another way. You see, I've just told you each of those is gravity. Each of those is the force of gravity. Well, if they're both the force of gravity, it seems to me that I can go like this. If they're both the same thing, McKinley, can't I say that they're equal to each other? I mean, if one's gravity and one's gravity, then they're equal to each other. And there's the little mass, the person on the surface of the Earth. Those are the same. Which I guess means that another way to calculate g without a stopwatch, without a scale, but to actually calculate it, an expression for g must be big G, mass of the planet, divided by radius of the planet squared. That is how we knew g of the moon before we went there. We could figure out the radius of the moon by looking at its shadow on the Earth, by looking at its curve. We knew that quite accurately. We could calculate the mass of the moon by looking at its gravitational effects on the Earth. And so before the Apollo rockets landed, they knew g on the moon was about 1.67. Didn't need to go there, because the problem with the first two methods is someone has to be there to measure it. That's how we also knew the gravitational field strength on Mars before we landed Mars rovers there. That's how we know the gravitational field strength of Jupiter if we ever do land something there. Although Jupiter being a gas giant, landing something there is a relative term. You don't really land, you sink. But we could. And this gives us something really, 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 really handy. I wrote down here. So, the gravity field, the gravitational field strength, is the property of a planet, star or moon, that depends on its mass and how far you are from the center. G, little g, equals big G, mass of the planet, or the star, or the moon, or the sun, or whatever, divided by how far away you are from the center of the planet. If you're on the planet's surface, then it's just the radius of the planet. But if you're up in orbit away from Earth, you can calculate what G is up there. G for the astronauts on the ISS is about 9.6, not 9.8. It's still there. Wait a minute, if it's still there, how are they floating? We'll talk about that later, but it's still there. It's a little less. In fact, G on Mount Everest is about 9.79. It's measurable as being slightly lower because you're a little bit further from the center of the Earth. Technically, you weigh lighter on Mount Everest. Technically. That's the gravitational field strength. And what are its units? Well, you can think of it as an acceleration, or you can think of it as force divided by mass, because F over m is also acceleration. Generally, Kyle, if I'm treating it as an acceleration, I'll use meters per second squared. If I'm using a force or I'm using it to find a force, I tend to write newtons per kilogram. I won't take marks off. Whichever unit you use, Emma, is fine with me. I'm a physics nerd. I'll try and use the right context in the right situation just because. So gravitational field strength. We can now calculate gravitational field strengths of planets. And it comes out of recognizing that gravity equals gravity, so little g must be the same as that. This last property is useful because it provides us with a means to calculate the mass of the Earth. I told you last class that how do they figure out how heavy the Earth is? It's not like they could put it on a scale. Once Cavendish had done that tension experiment, I showed you the short little video of the twisting. Once he had found that 6.67 times 10 to the negative 11, one of the first things he did was this. He said, well, I know this. He said, I want to get the m by itself. I'd like to know how much the mass of the Earth is, because we didn't know at that time. We had guesses, and all our guesses were taking shovels, big shovels, figuring out their average mass, and then using that to roughly take a best guess as to the volume of the Earth and saying, okay, if I know what one shovel weighs, how many shovels fill up the Earth? That was our best guess as to the mass. Easy to do, but it was way off. How would I get the m by itself? What am I going to do with the big G first of all? Divide. What about that r squared? What's it doing to the m right now? It's dividing, so how will I move it over? So Cavendish said apparently the mass of the Earth is going to be little g r squared divided by big G. Cavendish was able to time an object falling in free fall. He knew little g was 9.8. They'd known that for a while. And you can get the radius of the Earth actually just by looking at the curvature of the horizon. It's not that hard to calculate. In fact, 2,500 years ago, Eratosthenes calculated the radius of the Earth, and he was within 98% accuracy. So we've known that for a long time. The radius of the Earth is 6.38 times 10 to the 6th. That we'd known for a couple of hundred years. And then he took this constant that he just found with his experiment. And he said, how much does my Earth weigh? What do you get? How much is the mass of the Earth? He didn't have a calculator. He had to do this using logarithms by hand. It took a while. Yo, I forgot a squared on the R. Is that what you were about to say?
Yeah.
Candy for you later. Remind me. There, that's better. Nope. I think you should get 5.98 times 10 to the 24th. Now, if you didn't get that, I'll come over and look at your calculator in a second. But we'll talk about how profound this was. So he got this. And that was wrong as far as he was concerned. So he checked his figures. You see, up until then, the mass that they had for the Earth was much lighter. Because I told you the way that they had calculated the mass of the Earth, they had dug a few thousand shovelfuls of earth, took an average mass for a shovelful, multiplied by the volume, which you can calculate if you know the radius. And their answer was way too light. Way too light. So he said, the Earth must not be uniform all the way through. Maybe in the core of the Earth, now what do we know? What did you learn in Science 10? What's in the Earth's core? A very dense iron core that's way, way heavier than a shovelful of earth. And this was their first inkling that that was the case, because something had to explain why the mass was so much heavier than the shovels that they dug up. And the obvious conclusion was, I guess the Earth isn't uniform. There's something heavy down there. That's all they knew at that time. But it was the first inkling that, you know what? If you keep digging, you don't keep running into dirt. You run into other stuff. The very beginning there of geophysics and geoscience. Kind of cool. Turn the page. You guys stay here. I'm just going to scroll back for a second. Looking at Newton's gravitational equation, this bad boy here, it seems to me, look up, that there are 1, 2, 3, 4 variables. G is constant. It's always 6.67 times 10 to the negative 11. But there are 4 variables. Jake, it seems to me then that I can give you any 3 and say find the 4th. Okay? By the way, I have your Go card. Can you remind me at the end of class? It was in my letter tray today for some reason. So, example. Suppose 2 objects have a gravitational force between them of that much. If mass 1 equals blah, 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 and mass 2 equals blah, 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 how far apart are the objects? What are they asking me to find here? Let's write down our universal gravitational equation. Juan, gonna make it? Big G, M1, M2 over D squared. All right. What do they want me to get by itself? What do they want me to find, Dane?
Distance.
What letter is that in this equation? What letter is it? D. Where is it? On the bottom. I don't like it on the bottom. I want to get it to the top. And the easiest way to do that, since it's dividing on this side, that's the same as what on the other side? Multiplying. That's the same as this. D squared. Don't write this down. Look up. Just hang on a second. FG, don't write this down yet, equals big G, M1, M2. Those are identical equations. They look different. What am I trying to get by itself?
Distance.
What else is on the same side as the D now? F. It's FG, but F. How would I move the F over? Okay, this you can write down. Hang on. Is that okay, Jeff? Yep. I did 2 steps in one. I hope I didn't lose you. Except, Trish, I want to find distance, and right now, you know what I have by itself? D what? Oh. How do I get rid of a square? Oh, it's all coming back. How do I get rid of a squared? Yoink. Yoink. Okay, let's write this. It's going to be ugly, but I can't say it's tougher. I'm just going to say it's uglier on my calculator, but we've done equations just as tough before. The distance apart is going to be big square root. Big G is always 6.67 times 10 to the negative 11. Oh, let me pause for 1 second. Look at your calculators. So some of you have G built into your calculator. So 6.67 times 10 to the negative 11. Mass 1, 1,200. Mass 2, 2,500. Divided by, and it says the force was 3.848 times 10 to the negative 3. I would type everything inside the square root, hit equals, and then go square root answer, because that's a fairly complicated expression. Otherwise, you'll be having brackets all over the place, and it'll be confusing. Having said that, I think I can type what's inside without brackets, because there's only one number on the bottom, if I use my scientific notation button. Square root of that. Do you get 0.228? That seems wrong. Let me double check. 6.67 times 10 to the negative 11, check. 1,200, check. 2,500, check. Divided by check. I've written it down right. Yes. Square root. Anyone else? Yeah, 0.228? Okay. Extend this a bit. If you, instead of doing 2 masses, hey, you could figure out how far away the moon was if you measured the gravitational force between the Earth and the moon. There are better ways to figure out how far away the moon was. Oh, but if you actually, we knew how far away the moon was before we knew its mass, so we actually used this to calculate its mass instead. We knew the force, we knew the distance. Hey, we can find its mass. If the gravitational force between 2 objects of equal mass is that much when the objects are 5 meters apart, what's the mass of each object? So again, we're using Newton's law of universal gravitation. I think this is our last question, yeah, and then we're into the homework. And some cool videos, good. What's this question asking? Well, you know what? Let's write down the equation. F equals big G. What's different about this question here? It says the two, what do you know about the masses here? They're the same. You know what? Instead of writing m1 times m2, I think I can just go m squared, because the masses are the same. It's mm, it's but even better, it's m squared divided by, really? Pen vanished again. Okay, pen vanished again, but now we're back. Yay, we are. What's this question asking me to find here?
Math.
How would I get the m by itself? What would I do with the big G? Divide it. What would I do with the d squared that I wrote so messily? Times it over because it's dividing. So if I hear you correctly, and I think I do, you're saying, hey, Mr. Dueck, if you want to get the m squared by itself, the f stays where it is. You're going to divide it by big G and times it by d squared. Of course, really, they didn't want me to get m squared by itself. Any suggestions? So again, what I said, Jake, is there's actually 4 variables in this equation. I'm going to say I think I can expect you to get any one of them, but I can give you any 3, find the 4th. And this is what we're doing with some of the astronomy stuff out there to find masses of stars and things like that. A little more complicated, but it's the start. Looks like the mass of this object is going to be the square root of the gravitational force, 4.6 times 10 to the negative 8. 5 squared divided by 6.67 times 10 to the negative 11. I kind of wish my calculator had that G button because that's a lot of typing. Again, I'm going to do what's inside the square root first, hit equals, and then square root. And I get 131 kilograms. Each. How does a black hole work? And what would it be like to fall into a black hole? Well, a black hole works when a star has enough mass that it starts to collapse on itself and its diameter, its radius, gets smaller and smaller and smaller and smaller and smaller, so small that it's nearly zero. When you divide by a really small number, what do you get as an answer? A big answer or a small answer? A huge answer. This is why black holes have such strong gravitational force. You're almost dividing by zero. In fact, the joke we make is black holes are where God divided by zero, is the joke we physics nerds make, because that's comes out of this equation. Divide by zero, this seems to be what's happening. You get a huge gravitational force. So what would it be like to fall in? Well, let's suppose you were going head first. As you got closer and closer to the black hole, the gravitational field strength would be so strong that the distance between your feet and your head would cause your feet to experience a different force than your head was experiencing. Your head would be experiencing a slightly stronger force. Your feet would be experiencing a little less force. And initially, actually, it would feel pretty good. It would be just like you were stretching. And what do we do first thing in the morning when we get out of bed? We like to stretch. It would be, But after a few more moments of falling, you'd have a situation that would make a medieval torture rack look like a child's toy, because the difference in force between your feet and your head would be such that you would bifurcate, that it would actually overcome the molecular bonds that hold you together. Somewhere right around your middle would, and then those pieces would, Not only that, though, it turns out that a black hole's gravitational field strength is so strong, it actually warps and curves space itself. So not only are you being stretched by the gravitational field strength, it turns out that your width is decreasing. It's warping space, and you're being extruded like toothpaste through a tube. And physicists have a name for this. We call this process spaghettification. That's what it's called. Falling into a black hole results in spaghettification, where you're both being made very, very long and at the same time being made extraordinarily narrow, and then being split into many, many parts. Not on your test, but how could I resist teaching you the word spaghettification? Homework. Number 1. 2 is good. 3 is good. 4 is good. By the way, we're done the unit, so the next couple of days is going to be review, another take-home quiz, some cool videos. I'm looking at your test not being next week, but probably the week after. Okay? Oh, sure, find a mass. Eight is physics 12. Sorry, 6 is physics 12. Number 5, I said find the mass of each. That's equal masses. Number 7 is unequal masses. That's good. So far, I'm assigning everything. Sorry, but we need to practice this. 10, I'll skip. 12 is good. 13 is good, except please notice that they gave you this in kilometers. You'll have to change it to meters. And 14, we'll skip 15. And I gave you a bunch of the masses of the moon and the sun. I think I also put these on your formula sheet. I can't remember, but I know I included them here as well. There's about 20 minutes left in class. I got some cool videos, but you know what? I'll show those next class. I'll give you, because you guys got a long weekend, as much time as possible to get the homework done.